Thanks. Thanks for letting me talk here and being willing to sit through this. So I'll try not to bore you too much. So this program is Equivariant Homotopy Theory in Context. And this is definitely pretty far over on the context direction, right? So this is, I'm going to be talking about a fairly geometric situation. I'm going to be drawing some pictures. And equivariant ideas like genuine equivariance and representations and stabilizing with respect to those are going to be present in the geometric situation. So it kind of parallels the things that you're seeing in equivariant algebra. And hopefully you will find that entertaining. So let's get started by letting M be a compact, smooth. So for now, non-equivariant. So compact, smooth manifold with corners. Okay, so it's a manifold, it's got a smooth structure, and instead of locally looking like Rn, it locally looks like 0 infinity multiplied by itself n times. So, some places it'll look like a manifold with boundary, some places it'll just look like a manifold, and then you'll have these corner points where, there's nothing to say other than it looks like a corner. Okay. So an h-cobordism on M is another compact manifold. I'll probably stop writing smooth, but it's also a smooth manifold with corners W. And I want the boundary of W. So if M didn't have any boundary, I'd want the boundary of W to just be M disjoint union something else. And then I'd say it's a cobordism from M to that something else. But now, since here I'm allowing M to have a boundary, I'm going to say that this is M, and then it's joined along the boundary of M with the boundary of M times I. And then so maybe that's boundary of M times 0 where it's joined. On the other side, it's going to be joined to some other manifold N. As promised, here's a picture. So here's M on one side. Here's N on the other side. So you think of this as the bottom of the cobordism. And think of this as the top. And then over here, I have the boundary of M times I. So I guess because this picture is so low dimensional, the boundary is both here and here. Multiply that by I. And you think of those as the sides of the cobordism. Okay. The definition's not done yet. That's part of it. Okay, so then plus, what else do I want? So I want, what do I want? I want W to be diffeomorphic to M times I near the bottom and sides. So I'm very happy you guys have colored chalk here. So there's a little open neighborhood of the bottom and sides. And on that neighborhood, I want to identify W with a corresponding neighborhood of the trivial cobordism, or the identity cobordism. That's M times the interval. So I'm going to identify it with this neighborhood here. It's kind of like a collar, but it's a little bit more than that, because it's like reaching up the sides. Okay, I also want all the corners of W to be contained inside the boundary times I. So basically there's no corners happening here, and there's also no corners happening here. Up here it's just manifoldiness. Just nice and smooth, no kinks.
What is the n different directions, are they distinguished?
No, they're not distinguished. So in the coordinate chart, oh yeah, so this isn't like an n-add. In the coordinate chart, you're allowed to, if you switch to another chart, you're allowed to rearrange the coordinates. Yeah. But this condition is quite strong, right? This basically says, okay, M is allowed to have corners, but then psych, like you're not going to be able to do anything interesting near those corners. So it's basically just completely trivial there. And the interesting bit where you're attaching handles and something k-theoretic is going on is like all happening in this GUI center here, right? It's not happening at the bottom and sides. Okay, and then finally, and the most important thing is that if you include the top and bottom, these have to be homotopy equivalences. That's what puts the H in h-cobordism. So, if you ignore boundary and corners, this is really just a cobordism from M to N. Right? It's just a manifold that goes from M to N. And it is homotopy equivalent to both M and to N. That's what an h-cobordism is. If you care about h-cobordisms, awesome. If you don't, you actually do, because so if you have two manifolds M and N, and you're trying to construct a diffeomorphism between them, and say we're in a high dimensional settings, like dimension 5 and above, the way that you typically do this is you start by giving a homotopy equivalence. Right? So you use algebraic methods, say, to prove that there's a homotopy equivalence. And then surgery theory turns that homotopy equivalence into one of these h-cobordisms. Right? Surgery theory never really produces maps. It only produces manifolds. So it takes the gap in between M and N, where this map is, and just fills that gap with a manifold. It's this is the kind of thing that shows up when you do that process. So you care about these, and especially you care about when are these trivial. In other words, when I have an h-cobordism W, when is that cobordism diffeomorphic to just M times I? Because when it is, then, hooray, you've actually made a diffeomorphism from the bottom to the top. And kind of in broad strokes, this is how we make diffeomorphisms of high-dimensional manifolds. Right? These h-cobordisms are an intermediate step in making them. OK. Right. This is also not quite the standard definition. I put corners in it. And that's a little bit non-standard, but I like it. And there is, I think, some very good reasons for doing this. But in case you've seen the definition before, you might have seen something like W is just a manifold with boundary, and M is a part of its boundary, and N is the other part. And then when you consider these up to diffeomorphism, you again take a neighborhood of M, and you're not allowed to move it. So maybe you've seen this definition before. The space of these, I haven't defined the space yet, the space of these is equivalent to the space of these. So basically, I'm not allowing myself to move anything near the bottom and sides. And so as a result, it doesn't really matter what happens there. This is the same space of h-cobordisms that you've seen before. OK. Actually, I should say what the space of h-cobordisms is, right? So there's a space, fancy H of M, of h-cobordisms. So you should think of this as it's a disjoint union over diffeomorphism classes. So I'll say that two of these are diffeomorphic. I can form a diffeomorphism, and it's the identity near the bottom and sides. Okay, that's an isomorphism of h-cobordisms. You can form a group out of that. And so if you take the classifying space of that group, one copy for every isomorphism class, that's what the space of h-cobordism should be. You can also describe it as a simplicial set. So it has a k-simplex for every e to delta k, which is a fiber bundle, so a smooth fiber bundle, such that the fibers are h-cobordisms. So you give this fiber bundle a structure so that on each fiber of this map to delta k, you're getting an h-cobordism. And in particular, along a one simplex, you can always trivialize these. And so along every one simplex, you're getting a diffeomorphism from the one over here to the one over here. OK. I'm going into a little bit more detail on this because, this actually, this isn't quite homotopy theory, right? This is differential topology at this point. But don't worry, it'll turn into homotopy theory soon. Okay, so that's what is a simplicial set. And we also have the stabilization map. So this is where the stable homotopy theory implicitly comes in. Given an h-cobordism on M, I can produce an h-cobordism on M times an interval. And you're supposed to iterate this and keep going. And as you keep going, you kind of see why it becomes natural to think in terms of manifolds with corners, because even if you didn't start with one, pretty soon you have one. In a lot of the literature, the way you get around that is you just keep rounding the corners, that you always stay in manifolds with boundary. But I don't know, I found that it's better to just let the corners be there. So I want to just go back and say, this is what an h-cobordism should have been all along. All right, so what is this stabilization? By the way, is this too low down? Should I move this board up? Looks good, okay. So what is the stabilization? So now let's drop the dimension of our pictures by 1. Okay, so now that's a cartoon of a cobordism W from M to N. So the stabilization multiplies that cobordism by I. See people moving their heads around. What's up? Oh, I have lots of space here. Okay. So we take W times I. Okay, so now what does that look like? Well, it looks like a bunch of copies of W. Right? And now I'm going from M times I to N times I. That's not quite right, though, because remember my condition, when I made the original definition, my cobordism has to be trivial on the sides. Right? So whenever I get to the boundary of M and I go up, I have to get the boundary of M times I. And that over there is not trivial, right? Okay. How do we fix that? There's kind of 2 standard ways to fix it. So one is to take W times I and bend it like this. Like that. So that's W times I. And then I'm going to glue something in here. So along the top, I have N times I. So in here, I'm going to glue in, use some colors. This is going to be N times this half disk. And then down below, this is an M times I down here. Down here, I'm going to put M times this shape, where I've taken a square and I've removed the disk from the top. So intuitively, you can kind of think of this as you're taking the bottom near the boundary of M, and you're kind of pulling it up. And so now you've arranged it so that here I have M times I. So it's trivial in this region, and then it's sort of trivial in this region. All right. Another way of doing this is I can take that W times I, but then I can take the whole top of it and crunch it to 1 point. So I get a picture that looks kind of like this. So I'm showing you these pictures because these are going to show up in the proof a little bit later. Okay, so now what is this region? This is W times I, but now I'm doing a quotient. I'm taking the N times I along the top, and then I'm gluing it down to N. You have to think a little bit about how do you make it smooth here. So you choose a collar at the top. If I take a part in the top of the cobordism that looks like N times I, that choice of collar gives me a choice of smooth structure here. And that depends on a choice, but the space of collars is contractible, so that's a contractible choice. And then you do the same thing down here. Exercise. Those two things are diffeomorphic. All right. that's the stabilization map. And using that stabilization map, we can talk about stable things. So we can let the stable h-cobordism space be the colimit as n is going to infinity of h-cobordisms on m times n intervals. It's a theorem of Aguza that this stabilization map, when I multiply by one interval, if the dimension of the manifold is n, this map is about n over 3 connected. And so similarly, the map from h-cobordisms to the stable space is also about n over 3 connected, plus a constant that I didn't write down in my notes. So I can stabilize in this way, and now this space agrees with the original space in some stable range. But because the dimension has gone to infinity, it gets easier to think about. OK, so a little while ago, I gave you the spiel about why you care about h-cobordisms. And in that spiel, I said the really important thing is that you understand if I give you an h-cobordism, like when can I make it trivial? Right? When can I say it's m times I, and therefore make a diffeomorphism from the bottom to the top? Right? OK, so the main theorem that governs this is the h-cobordism theorem. So this is a theorem of Barden-Maser and Stallings. It tells us that pi naught of this space, in other words, h-cobordisms with m as the base up to diffeomorphism, is isomorphic to the Whitehead group of M. And when M is connected, in this theorem, I need the dimension of my manifold to be at least 5. It also works if the dimension of the manifold is less than or equal to 2. Basically, as long as 4 manifolds are not, as long as there's no 4 manifolds, like M is not a 4 manifold and the cobordism is not a 4 manifold, the theorem is true. Otherwise, it's false. OK, and this is when M is connected. This is expressed as a form of K-theory. This is the K-theory of the group ring, modulo plus or minus the trivial units. This theorem is telling you that this question of, OK, I have this cobordism, when can I trivialize it, becomes an algebraic question. Right? I just have to look at its image over here. I get an algebraic invariant. When that vanishes, hooray, I made a diffeomorphism. So this sends each cobordism to its Whitehead torsion. So you can think of this as kind of saying the pattern of how handles are attached to make the cobordism forms some invertible matrix. And that matrix is invertible, but can it be reduced to the identity matrix by row operations? Basically, it tells you, can you slide these handles around in a way to cancel the critical points? OK, but the point is this geometric problem has an algebraic solution. And so this Whitehead torsion is 0 if and only if your cobordism is trivial. OK, so that's all well and good for saying that there's one diffeomorphism, but we're homotopy theorists, right? We like to understand the space of diffeomorphisms, right? Given 2 diffeomorphisms, are they isotopic? You know, what's pi1 of the diffeomorphism group, and so on. So that turns out to be governed by the higher homotopy groups of this. Right? Not just pi0, but also pi1, pi2, and so on. And so what you would like is a theorem that's like this, but that also tells you about the rest of the space. OK, so that's the parametrized h-cobordism theorem of Waldhausen, Yarn and Rognus. And it expresses the space, instead of expressing it in terms of K-theory, it expresses it in terms of Waldhausen's A-theory. So a different form of algebraic K-theory. Okay, so that one says that there's a fiber sequence, suspension spectrum of M, goes to A-theory of M, goes to a spectrum called Whitehead diff. So this is a fiber sequence. And that furthermore, if I take this spectrum, and I take its infinite loop space, and then I loop it one more time. So this is a setting where infinity plus 1 does not equal infinity. Then this is the stable space of h-cobordisms. Okay, so it tells me that h-cobordisms, if I'm willing to stabilize in this way, are completely described in terms of algebraic K-theory. So this cofiber of spectra, this map actually splits. So it really is A-theory modulo a summand of A-theory. Okay, and on pi 0, this theorem does imply that theorem. Right? It really is a lift. Pi 0 of this space corresponds, because of this extra loop, to pi 1 of this spectrum. And so pi 1 of this spectrum is pi 1 of K-theory modulo pi 1 of stable homotopy. We're in the range where this is the same as K-theory of a group ring, and stable homotopy gives us that part.
In what categories are splitting?
In spectra. So these are spectra. And then I suppose that also means that there's a splitting once you take infinite loop spaces as well.
This context category could also mean topological is plus linear or differentiable, and in that case the answer is differentiable.
Oh, yes, thank you.
You answered the question I meant to ask.
Yeah, if this is PL or top, there's a similar theorem, but now this isn't just stable homotopy. This is stable homotopy smash with A of a point, and then that one doesn't split.
Are you saying that the splitting is somehow less natural or something?
The splitting's fairly natural. It arises from the Dennis trace. You go to the free loop space of M, and then you evaluate at the base point. All right. Great. So that's the non-equivariant theory that we want to generalize. So we're here, right? Great. We all agree that we're here. So therefore, I should write G on the board, right? That seems sensible. And maybe I should even write some subgroups of G on the board as well. Great. OK, so let G be any finite group. And I'm going to have G act on the manifold M now, smoothly. And I'm actually going to do a little more, because I insisted that my manifold has corners. I'm going to insist that locally, my manifold looks like G times over H with an H representation V times some corner coordinates. So here K is less than or equal to N. V is some H representation. And of course, H is a subgroup of G. G is never allowed to be a subgroup of H. That's blasphemy. All right. So I'm going to assume it acts smoothly. If there weren't corners, this would automatically be true. Right? This is what the local model for your manifold would look like. But the notable thing about this is that I'm going to have G not act on these coordinates. Okay, so in other words, the G action is going to be trivial along the corners. And that means that I'm going to not have situations like this, where I have a corner and I'm flipping the corner. No. Bad. Do not want. I want this because I'm going to want the H fixed point submanifold to be a submanifold that's neatly embedded and has a tubular neighborhood. And if you imagine like flip along this with fixed points going along the middle, that's not going to have a nice tubular neighborhood. But this is fine, because I really care about G manifolds with boundary and their products. And if you take products of G manifolds with boundary, you always get something of this form. Okay. Great. So now, feel like in this crowd this is going to be a little bit silly to write, but let me write it anyway. So MH is the fixed points. Right, so these are the points where the stabilizer, where H is a subgroup of the stabilizer group. I'm going to let M sub H be the H stratum. So these are the points where H is equal to the stabilizer. The points that are fixed by exactly H and not a bigger group. I'm going to let WH be NH mod H. That's the Weil group. The Weil group acts on the H fixed points. Right? That's why I care about the Weil group. And its action on the H stratum is a free action. Right? Those are exactly the points where H is the stabilizer. Okay. Okay, so suppose, I'm going to go back up now. I'm going to remind you next what an isovariant map is and an isovariant homotopy equivalence. Okay, so an equivariant map, F from M to N, is isovariant if, in addition to being equivariant, when I apply it to the H stratum, I land in the H stratum. So in other words, points that are fixed by exactly H have to go to points that are fixed by exactly H. If this were equivariant, they could go to points that are fixed by bigger subgroups, right? So you think of an isovariant map as a map that's both equivariant and stratification preserving. And then an isovariant homotopy equivalence. You just kind of follow your nose on this. So it's an isovariant map back. I'm going to avoid using the letter G for it. And homotopies to the identity. And all of these maps and homotopies are isovariant. So they're equivariant. They preserve the G action. And in addition, they're preserving the strata. So in particular, you're going to get homotopy equivalences on all of the strata individually, not just the fixed points. Okay. And then an equivariant, respectively an isovariant, h-cobordism, is one in which, so you have the same definition as before. You have a manifold with corners, you have the bottom, the top, it's trivial on the sides. But in addition, when I say M into W or N into W, I'm going to ask for that to be an equivariant homotopy equivalence, or respectively, an isovariant homotopy equivalence. Okay, so it's one in which these maps from M to W and N to W are equivariant, respectively, isovariant homotopy equivalences. Abbreviating here is hard because equivariant and equivalence start with the same 6 letters. So basically, in the setting, there's 2 notions of h-cobordism now, right? It's not, so, okay, I have homotopy equivalences. Well, great, what do you mean by that? There's 2 different notions. So why do we have 2 notions? Well, it's kind of, go back to why we care about h-cobordisms, right? We care about them because we want to trivialize them. And if you have an equivariant h-cobordism and you want to trivialize it, it certainly has to be an isovariant one as well. Right, so if you're trivial, in other words, if you're M times I, that implies that you're isovariant, which implies that you're equivariant h-cobordism. And in general, those inclusions are strict. We can go back So equivariant does imply isovariant if M has weak gap hypothesis. So that means that if I have an inclusion of fixed points that is proper, and where this component is actually touching that component, then the difference of dimensions has to be at least 3. So basically, when I go from smaller fixed point submanifolds to larger ones, I'm always jumping up by at least 3. Okay. So just like in the case without a G action, right, we care about these. You care about these. And the big thing that you care about is when can I trivialize them? And more generally, like what is their classification, right? What algebraic invariant do I look at that tells me if it's trivial or not? Okay, so that's given to us in 2 theorems. One is a theorem of Araki. Oh, good. Araki and Kawakubo. And the other one is a theorem that is independently due to Browder and Quinn, and also Rothenberg. All right, so let's do the Araki-Kawakubo one first. So this one says, if I look at equivariant h-cobordisms on my manifold, and I mod out by diffeomorphism, and I also mod out by multiplying by representation disks. Okay, so you go back to the stabilization map from before. Just do it over here. Remember, the stabilization map was I multiply by the interval, and then I kind of like bend the things up. You can do the same thing where instead of multiplying by an interval, you multiply by the unit disk of a G representation. Right? You multiply by the disk, and now again, I mean, you need more hands now because it's higher dimensional, but you need to like pull all the edges of the disk up in order to make your cobordism trivial on the sides. Okay, so if you take these equivariant h-cobordisms up to isomorphism, and you also take them up to the stabilization, then they're classified by the equivariant Whitehead group, WHG of M. And so what is this? So again, this is if M is sufficiently connected. Oh, no, it's not. It's just Whitehead groups. Great. This is always the splits. It's a direct sum over conjugacy classes of subgroups of the Whitehead group of the H fixed points, and then I take homotopy while H orbits. Okay, so we're getting to the part now where the geometry is starting to mimic the things that you commonly see in equivariant algebra, right? We didn't even rationalize, and we're getting a splitting, and there's one summand for each conjugacy class of subgroups. There's fixed points, and there's homotopy while group orbits. All right. There's no assumption on dimension of M here because it's getting stabilized. Right? So if you multiply by lots and lots of representation disks, the dimension gets big. Okay, so that's one of the classification theorems. It says this is the algebraic invariant that tells you what are all the possible cobordisms. So now the other ones for the isovariant ones, Browder, Quinn, and Rothenberg. So this one says, if I take isovariant h-cobordisms on M, just up to diffeomorphism, so I'm not stabilizing them. So since I'm not stabilizing them, I have to assume something about the dimension, right? The assumption is if the dimension of all the fixed point submanifolds are all at least 5. So if you have like G fixed points inside, that has to be at least 5-dimensional. And then of course, everything bigger than that will be at least 5-dimensional. Okay, so in that case, this is isomorphic to another sum over conjugacy groups, conjugacy classes of subgroups of G, of the Whitehead group of, take the H stratum of M, and then mod out by the Weil group. So it's almost the same expression, only this is the fixed points, and so I have to take a homotopy orbits because it's not free. This is the stratum, and now the WH action is free, so I can just literally quotient out by this group. Okay, so there you go. So basically, classifying these splits apart into a bunch of non-equivariant problems. Right? You get some non-equivariant torsions that if you calculate and if they're zero, tell you that your cobordism trivializes, and woohoo, you have an equivariant diffeomorphism between your manifolds. Okay. So what about the space of diffeomorphisms, right? What about this result? Can we go above pi naught? Oh, by the way, so as an aside, so the Browder-Quinn-Rothenberg theorem implies the Araki-Kabakuo theorem. This theorem implies this theorem. So why is that? Well, it's because of 2 points. So one is, if I keep multiplying by representation disks, and I let V go to infinity, or maybe that's bad notation, maybe I should be saying it's going to a complete G universe. Right? I'm adding in infinitely many copies of all the irreducible representations, then M times dV eventually gets the gap hypothesis. You're using non-trivial representations, and so there's a difference between the fixed points and the whole representation, and that difference in dimensions adds to your gap. So if you stabilize, you eventually get into the point where you have the gap hypothesis, and therefore, oh, yeah, up here. Therefore, equivariant and isovariant become the same thing. Right? The classification of these is the same as the classification of these. And then the other thing, which is kind of a fun fact to think about, if you think about the H stratum of this space, including into the H fixed points, the connectivity of this map goes to infinity as the representation goes to infinity. So the stratum becomes a more and more highly connected subspace of this. And then, of course, this space, now that we're just taking H fixed points, is equivalent to the H fixed points of M.
This kind of M cross dV. I mean, are you also having to deal with M cross dV1 cross dV2 or not?
Oh, yes. So you're right. I'm being a little bit sloppy about that here. If you multiply repeatedly, then yeah, you're actually multiplying by dV1, dV2, dV3, and so on and so on. It turns out to not matter that much because you can take a product of 2 disks and embed it into a larger disk. And then if you do that, you extend the cobordism by a trivial cobordism there. You get the same operation as if you had just multiplied by the big disk. And so for that reason, up to homotopy, multiplying by 2 disks is the same as multiplying by 1 big disk. That's a great question. In here, and as V goes to infinity, this expression turns into that expression. Okay. So now if you didn't care about isovariant h-cobordisms before, now you do, because right, this is the key thing. If you understand isovariant h-cobordisms, then you understand the equivariant ones up to stabilizing. Okay. So let hg of M be the space of isovariant h-cobordisms. So by the discussion that we just had, this is the only space we really have to think about. If we understand this, then we'll be able to understand the equivariant space as well. And let's let hgu be the colimit over finite dimensional subspaces of some complete G universe of h-cobordisms on M times dV. And again, as Neil pointed out, this is not quite an honest definition. You really want to take a co-limit over compact manifolds embedded in this universe. So that's a more honest way of writing this. But you can, as a cofinal subsystem, you can imagine I'm just iteratively multiplying by disks of representations. Okay. And so our goal is to understand this. So what are the homotopy groups? And is this related to algebraic K-theory? Is it related to an equivariant form of algebraic K-theory, like in the Waldhausen-Jahn-Rognus theorem? Okay. So here's the theorem. And this is with Goodwillie, Guguza, 2 dashes, and Merling. So just like for the Browder, Quinn, and Rothenberg theorem, we're going to assume that the dimension of each of our fixed points is at least 5. Okay, so here's what the theorem says. So this space of isovariant h-cobordisms is a product over conjugacy classes of subgroups of h-cobordisms on the H stratum of M, and then I mod out by the Weil group. Strictly speaking, that's not a compact manifold, but I'll show you in a little second. You can shrink it a little bit and make it into a compact manifold. Okay, so this whole space splits apart as the product of those spaces, lifting the result on pi 0, right? Saying this over here is pi 0 of this space, splitting apart into a product of those groups. And then furthermore, if we stabilize, that commutes with this decomposition. And so we get the stabilization of these, which becomes MH homotopy orbits by WH. Okay. So basically, we get the same statement on the space that we got on pi 0. It splits apart as a product. All right. I was hoping you'd notice that. Isn't that strange? We'll get to that in a minute. So let me just briefly mention, this theorem is the main thing that you need to relate this space to algebraic K-theory. Like once you have this theorem in place, you can actually deduce the equivariant version of Waldhausen-Jahn-Rognus from the non-equivariant version. So why is that? So your goal is to make this fiber sequence where the other two terms are, so I'll write things in terms of infinite loop spaces now. I take the suspension spectrum of M, I take its genuine fixed points and take the infinite loop space of that. Genuine fixed points and infinite loop space commute, so you can put those in either order. And then I have the infinite loop space of some form of algebraic K-theory. So Mona and I wrote this down, what this spectrum is. This is an equivariant form of A-theory. And the theorem is that you get a fiber sequence like this. So in other words, h-cobordisms, so the equivariant kinds now, stabilized, are expressed in terms of algebraic K-theory in much the same way that it was non-equivariantly. Okay, so I claim that this is just a corollary. Why? Well, the idea is by this theorem, so by Gim, this splits apart as a product of non-equivariant, so H infinity of these spaces. There's a pretty famous theorem in equivariant homotopy theory that suspension spectra, when you take their genuine fixed points, that splits apart, right? That's the Tom-Dieck splitting. So that splits apart as a product. If I write this in terms of infinite loop spaces, omega infinity, sigma infinity plus of MH homotopy while H orbits. And then there's also a result over here. This is from a paper of Badziak and Dora-Biala. That this form of K-theory, when you look at its G fixed points, that also splits apart. Everything's an infinite loop space here, so I'll put omega infinity of A theory of this same space. And so now, okay, so this whole thing is just a product of copies of the non-equivariant fiber sequence. Right, so that's why this proves the theorem. All you have to know is that this decomposes in the same way that these two spectra already decompose. Cool. All right, maybe I'll put that up here.
Are you saying you have a spectra, or what are you saying?
This is just a fibration sequence of infinite loop spaces of the G fixed points. It would be great to add more structure to that, but that's what we get for now. Yeah. I mean, one can certainly think like, well, I've stabilized by representation disks, and so I get the kind of operatic structure on that stabilization, using configurations of points and representations, like exactly the kind of structure you'd need to de-loop that h-cobordism space. And so then you can start to ask how that spectrum compares to the K-theory spectrum. My understanding is that actually in the non-equivariant case, that is already quite a challenge. But that is definitely a thing that we would like to know. All right, so that's kind of the rundown, right? So in summary, right, why we care about h-cobordism spaces, how they relate to algebraic K-theory, what happens equivariantly, what kind of the main result is that you need to know equivariantly, like how does it reduce to the non-equivariant statement, and then what can you conclude from that? All right, so in the remaining part of the talk, I want to draw some pictures about how you prove this. All right, so the main concept in the proof is that there's this more general stabilization. I mean, this is actually an idea that I think is pretty well known, but sometimes challenging to write down really carefully. So let me just describe it. Oh, yeah. If I have any equivariant embedding from one manifold, let me call it M0, into another manifold, M1, then I can define this map of h-cobordism spaces from cobordisms on M0 to cobordisms on M1. And in the special case that this is M0 includes into M0 times a disk, that this is the stabilization we've seen before. Okay, so I'll just draw a picture. Okay, so here's M1. Here's my embedded copy of M0. This is a smooth embedding, so it has a disk bundle. It has a tubular neighborhood here that looks like the unit disk of the normal bundle of the embedding. So sorry, the unit disk bundle of that. Looks just like that. And then I have, really want blue. Blue needs some love. Okay, and then I have this cobordism, W, that is a cobordism on M0, so it's just kind of sticking up straight out of this picture. And finally, that cobordism is trivial near the bottom and sides. So on that region, it looks like M0 times I. Okay, so now what does this map do? Let's go over here. I think I can fit it over here, actually. Okay, so what does the stabilization do? Draw M1 again. Well, it kind of does this picture from before, but I'm going to swing the cobordism back and forth like this. So I'm going to form a picture that looks like this. Okay, so this looks like W fiber product over M0 with D nu. That gives me kind of this band, and then I crunch the top of the band back to N. So along N times over M0 with D nu, this gets glued back to N. So it's kind of like multiplying by a disk. Instead of just multiplying by a disk, you're taking a fiber product with a disk bundle. Okay, that produces a thing that is now the trivial cobordism all along here and all along the edges and this face here. It's all trivial because I took something that was trivial here and I kind of swung it around. So now that it's trivial in that whole region, I can now just fill it in and make something over the rest of M1 by just making everything else the trivial h-cobordism here, M1 times I. Yeah, so that defines a stabilization map. You think of this as making h-cobordisms into a functor along embeddings of manifolds with corners. Okay. So now, take your manifold M. Actually, let me make it bigger. That's better. Okay, so now take your manifold M, and now take the fixed point submanifolds one at a time. So say I'm going to take Mg. So starting with the smallest ones and going up, remove tubular neighborhoods about them, and then intersect the result with the next level of fixed points. Okay, so say these are the G fixed points. Say these are the H fixed points. I'm going to take the G fixed points. I'm happy with that. But I'm going to take the H fixed points, and then I'm going to like remove this tube about the G fixed points. I'm going to call that M sub H in brackets. So in general, M sub H in brackets is going to be the H fixed points, and then I'm going to mod out, or I'm going to subtract, rather, an open tube about the K fixed points for all K containing H. So in this way, I'm going to end up getting something compact again. In fact, I'm going to get a manifold with corners. Oh, another place where corners naturally show up. So you can see that here I have the H fixed points, but now if I remove the G fixed points, I get the H stratum. But if I remove this tube, now I'm going to get something that has a boundary. Okay, then I remove a tube about this. I maybe draw it here a little bit better. I remove this tube around this. So now see it's making a corner here. And then everything that's left, so there's no other fixed points, that's going to be M for the trivial group. Similarly over here. So in this way, I'm kind of carving up the manifold into pieces. And now each piece is a manifold with corners that has been embedded in. There's this big purple piece, there's kind of this brown piece in there, and then there's this green piece in the middle. Okay. So altogether, that gives an embedding from the disjoint union over all the subgroups of this M sub H brackets into M. That gives us an embedding of manifolds. Okay, now hit it with this functor. So now I get hg of this disjoint union goes to hg of M. And if you think about what this looks like, this breaks apart into a product over conjugacy classes of subgroups, right? Conjugacy because G is taking different subgroups to other ones conjugate to it, of cobordisms on WH equivariant cobordisms on MH brackets. And then you can further write this. I can take the WH and just put it in here as orbits, because now it's a free action. You have cobordisms on a space with a free group action. It's the same thing as cobordisms on the orbit space. Yeah, okay, so that's the map. And it's a map from the products to the space. That's the map that's the equivalence. All right. I think I'll just end. I was going to say a little bit more about how you prove that this is an equivalence. The idea is by induction up the strata. And there's a little bit of a subtlety, because you'd kind of think like, oh, I'm just going to take fixed points in my cobordism, and that'll give me the cobordisms on each of the pieces. But it doesn't quite work out that way. There's a bit of an issue that when you go back and forth, you end up creating a cobordism that is non-trivial on the side. So like say I take a cobordism and just restrict to the fixed points. I get a cobordism on MG, that's totally fine. But if you drill it out, what you have left here, there's no reason it has to be the identity on the side. And so there's a little bit of jumping back and forth showing, there's a little bit of jumping back and forth in order to compare the fiber sequence you get from stratifying this against like the trivial fiber sequence that gives this product. And that comparison, you end up adding cobordisms and then adding negatives of the cobordisms to cancel them out. And that is exactly where the dimension assumption shows up in the proof. Right? Like you can construct this map without any assumptions, but the fact that it's an equivalence uses the proof, uses that assumption there. Okay, I think I'll end there. Thank you.
Any questions? When you're comparing G fixed points and H fixed points, I mean, there will typically be representation spheres in normal directions. But I guess when you're taking human neighborhoods, you're only sort of looking at a radial. I mean, the thing you're cutting out, the corner arises only because you're putting some bound on the radius in that representation sphere. Is that why you get a? I guess I'm just asking why, if you could say why you.
Like why you get corners when you do this?
Allowing rather than more complicated corners.
Oh, why do you only get the simple kind when you do this? Yeah, so like when you remove this first tube, you're gonna, say that there is no corners to begin with. When you remove this first tube, around the frontier of this tube, the direction that goes across this is like the radial direction in your representation. And so G is acting trivially on that. And so now you have something where G is acting trivially, and now every time you create a new direction, well now here I'm looking at the representation for the disks that are normal to this manifold. And again, the new direction I'm creating, G is acting trivially on that direction. And so that's why as I keep doing this, I keep getting G trivial corners. Yeah. I should have also mentioned, it's kind of fun to think about what the image is under this map. Right, like picture a cobordism on this part. It's the identity near the boundary. Picture a cobordism on this part. Now swing it around to make a cobordism on this tube. Now take a cobordism here. Now like swing it around, right, in 2 different dimensions to make a cobordism on this. And now they just like neatly all pack together. It's like a bento box. Like every little thing just like neatly fits up like very snug against everything that's next to it. And the fact that this is equivalence is basically telling you every cobordism on this space is equivalent to one of that form. Right? We have these nice little pieces that are neatly packed together like that.
Any questions? Well, it's like Cary again. Great.
Thanks.